Hi, my name is Dennis. Welcome to Foundations of Networking, Troubleshooting Connectivity Issues. Today we're going to learn a little bit more about the objectives of finding errors at different layers of the OSI and how to align them and really try to understand what part of the OSI layer that we need to start off with. We're going to utilize tools and troubleshoot connectivity problems at different layers. So layers 4 and layers 3, sometimes 2 and layers 7 primarily. And we're going to apply mitigation and architectural best practices and knowledge to help mitigate some of those issues around connectivity problems and to create best practices around security as well as resiliency in the near future for your applications. So let's look at some common troubleshooting use cases. First and foremost, let's get a refresher of the OSI model. We have 7 different layers: the application layer, presentation, session, transport, network, data link, and physical layer. Now notice that they are all in different colors, and so layers 5 through 7 are really at the application layer where you'll be doing most of your troubleshooting at from a network perspective. On the transport and network layer, which is your IP addresses and ports, think about firewalls, think about stateful connections, netcat listeners, and then at the data link to physical layer, these are really close to your end. Client side, server side, is there a physical connection problem? Is there perhaps an ARP issue? Do you even have an IP address at layer 3 and layer 2 to actually make a resolution for? So you have to understand the process of elimination. If you have a particular issue where the connection is not being made at TCP at a lower level, and so we'll grab this here. Let's say TCP lower level. If the port is coming back saying closed, do you really think you have to start off up here? No, you need to start closer down here, layer 3 and layer 4, and understand that if there's a firewall rule in blocking in place, or if there's a connection timeout issue, do you even have a route? Similarly enough, if you have no ARP, no IP address, and you're not finding a link light, perhaps you have a physical connection issue. Of course, let me erase that real quick. Perhaps you have a physical connection issue where you have to look at termination. So usually you're starting at the top or you're starting at the bottom. So even though these are distinct layers, these are a good way to have a framework for understanding what and modeling what your normal behavior that you looked at previously with these layers to see where you can actually start troubleshooting at the best approach. Here's one case. We have an HTTP, which is obviously a layer 7 application. We have some unauthorized status code information right here. And so thinking back to our concepts of what normal behavior looks like, a response always has a status code, one status code for every request. HTTP4X means that there's something that happened on the client and that is not a server-related issue. It's an issue related to the original request, such as login password failures. HTTP5X is really server-side issues, which denote more of the application that has gone wrong from a logic perspective, or other errors such as too many API calls to it. Here we see in the full log, you are not authorized to do invalid credentials. Now, if you saw a whole bunch of these in a very short time span that is beyond your normal course of day-to-day operations, maybe that's something that you might look into from a security brute forcing perspective, or if service account information changed on the back end. How about layer 1? Notice that we have no link light right here on this next port. Could be an issue with termination, not at the protocol level, but at the actual physical medium level. Here we see below, which is the 568B standard. B stands for building. Orange, white, orange, green, white, blue, blue, white, green, and brown, white, brown. For those of you who haven't done network cabling in the past or have worked in data centers or infrastructure, you probably memorized this and forgot about it. But for those of us who have worked in there many years, this is something we memorized quite a bit. Now, without the 2 lights, now I know that there's an issue either with the hardware at the port, the medium, or perhaps on the other side where the other network card is not providing signal. Either way, you got to look into it and do some double checking. Sometimes network switches are not having an issue, but maybe you have to enable the port physically before it can actually have connectivity to it. Let's look at TCP in terms of what kind of normal behavior patterns we should expect for troubleshooting. With an open port, we have a full connection with a 3-way handshake, which is A right here. With a closed port, we have two different options. We have a reset sent from the endpoint host, or from a router port unreachable via the ICMP as a message, or perhaps host unreachable non-existent host. Again, also being sent from the router, or there's also a fifth one, timeout. No response whatsoever. And this could be a blockade on the firewall at the host server side, or at the network layer, firewall or router in between. This is really great for understanding that if there's closed ports, but if you do have an IP route that goes with it, you could have filtration at the OS, the firewall, and other software-related items. What about missing data with TCP? What is considered normal if there's a packet drop and their connection is having issues, such as slow connections or constantly retrying connections? Well, one might be if I lost segment 1 in transit for the response, client 2 or the client is going to say, hey, I acknowledge that you need to send me segment 1 over and over again. By default, the limit retry is 3, and depending on your stack, either at the network and at the OS layer, it could be as long as 5 minutes between network connection timeouts and retries. You really have to understand that if you see a bunch of acts with the acts not incrementing and the segments not incrementing, then you need to really look at what's being dropped and if there's a continuously large drop rate. To see what kind of drop rates there are at the packet level, ifconfig might help you, and ipconfig, if you're on Windows, /all, will give you these statistics on your interface for possible issues at the network card issue. Now, if there's drops going on in between for the internet, and you're getting lots of trace routes missing with stars in them without any kind of timeouts, perhaps there's a network issue that you can't fix. There's a lot going on in the internet. This will help you narrow some of that down. Another thing to think about is that what's normal for UDP? It doesn't require a response to be open. And that's why when we look at Nmap, sometimes if you use a scan, it's going to say, hey, I have an open/filter because I don't know, because it gave me no response. However, if I do a service scan, sometimes I can actually see data being responded back to me, and that's why I know for sure it's open. Now, if you use NCAT or any kind of netcat listener and client, you need to have to speak and send payload that makes sense to that application. So if you're doing a DNS query, you wouldn't send a hello get / that's HTTP, and you might end up with an error or a closed connection, which you don't know at that point what's going to happen. You can also get ICMP related messages in addition to no responses coming from the layer 3 routers. You rarely see those anymore. That's largely because of enumeration and network mapping use cases for that and TCP to make sure that attackers don't get a good map and understanding of your network. Now, ICMP, like I said, is a helper protocol. It can give you different error messages as required, but you can also utilize it for understanding latency. So here I'm pinging google.com, and my latency is under 100 milliseconds, which is good. There is some variation depending on the 4 packets that were sent out, but none of that was lost. All of them were received back with a maximum of 21 milliseconds, an average of 19. I can also use ICMP with traceroute. So as I increment those TTLs, I can also get the latency information on average right here. The higher the latency, which is usually the further the distance is, or if there's a major problem such as 200 milliseconds in between, maybe there's a router issue at the Comcast side in this case. When you utilize ICMP whenever possible, to help you with diagnosis and messages because it's a light protocol and doesn't require any ports to be open. However, ICMP is also becoming a rare factor in that not everything is going to be pingable from the outside. Keep this in mind that you might want to use traceroute, especially the Linux version of traceroute that has TCP UDP checks on always open ports. So you have a web server, for instance, you want to use 443 or 80, or you have DNS 53 makes sense to you. Here's another one. HTTP. What's normal when you send an incorrect address or an incorrect HTTP method? So in here, I'm starting with an HTTP post. I'm saying, hey, maybe get the maybe the API or the web page only supports a GET. Well, I'm getting a 404 not found, which is typically not the case. If you went to the browser with ifconfig.io, it'll give me a web page. So in PowerShell, invoke web request is the equivalent of curl. How about if I change the method to GET, which is the default? Now I'm getting a 200 OK as my status. So making sure that you understand the actual payload as well as the HTTP methods, having the right headers and all that other information is really essential for understanding that if you have HTTP as a protocol issue or as a client issue. Again, 400 series, it's a client issue, not a server issue, unless it's 500 series elsewhere. How about protocols with certifications, certificates like SSL or TLS or Secure Shell, SSH? Well, they create keys, they exchange the keys, and you connect to a public key and you have a private key, and that's your authentication or your encryption tunnel. Here's the problem with that. You have to have that trust. So if you don't have the private key trusted, or you don't have the public key trusted on your client side, you might get a message like this. Now think about Internet of Things, IoTs, Ring doorbells, drones, security cameras. What happens if they use SSH for authentication and encryption, and those keys are not trusted? The connection will stop. It'll fail. And so if you don't have access to the console or easy access to be remote over other means or mechanisms, you might be screwed up. Because why? You just send out a whole bunch of appliances and devices that cannot connect back to your cloud because you don't have a trusted certificate in there. So when you're troubleshooting connections, always look at the encryption's trust certificates, making sure that the trusts are properly installed and validated for each client as well as the server. Otherwise, you'll have no connection whatsoever, or a TCP reset at minimum. Now, this is not so much about protocols anymore. We need to understand also about troubleshooting connectivity at logging level. So what the application does. We saw application protocol level, but not the application logs themselves. Logs are really important in terms of troubleshooting as well as security purposes. The most important thing is, especially when you're doing multi-geographic regions, is that you need to account for time zones. The best practice is to always use UTC or universal time. For instance, I'm in -6 usually because I'm in the central time. Whoops, I circled 8. Let's circle 6. So I'm usually in plus or minus 6. -6 or -7, depending on my daylight savings time, because I'm in central time zone for that. UTC always is based on UTC 0, and so you could convert those later on if you needed to think about it in a different way. But logs have a synchronization of time and dates in a proper format, especially if you're doing a 24/7 operation. Now, speaking of time and date, you also have to have a time server. That's right. Just like your cursor is in your clock for making sure the time is staying in the heartbeat, you have time servers just like DNS servers. These are helper protocols operating by default on UDP port 123, sometimes on TCP port 123. This allows you to stay within milliseconds at a time so that logging and timestamps for your client and your servers are the same, and ensuring that there's no offset and highly accurate logs to start with. If you have a high performance application with millions of users at a time, every millisecond counts. And so you don't want those drifting away from each other. You don't want a 2-second interval because a lot of traffic can happen in that time period. Correlate your logs over using tools like log management solutions or scenes for security people. Examples might include a Logarithm, QRadar, and many other ones that can actually ingest logs at a higher state and large capacity. Speaking of logs, we want to have network traffic, but isn't network traffic really, you have as much throughput as you have to save for a network DVR for PCAPs? Of course. To solve this, we have network flow logs, and these are called flow logs with tuples. Notice your tuples are source and destination IP addresses and ports, along with the applicable protocol information, and of course, a reject or an accept as accordingly. As you see here, this is a version of Amazon Web Services version of flow logs, but there are many other types too, such as IPFix, NetFlow, and NetFlow is a commercial one from Cisco for their appliances and licensed to them. Other flow logs are considered open and no licensing required, so it gives you metadata detail about the connection, the bytes, as well as the direction, so you can actually make inferring judgments based on proximities and anomalies, as well as size and baseline. Remember, this is all about layer 3 and layer 4, according to flow logs. Instead of having decryption and termination at the network layer, you could also have application logs for every request, as well as the response that goes with it. Now, this doesn't give you everything. This gives you the header request and response. All the other payloads that go in between, that may not be part of your web server logs unless you enable it. But the advantage here is, just like with network flow logs, you don't have to keep large sums of data with you. It's compressible, and there's no protocol termination according to it. You can have server-side collection instead of relying on client-side connectivity for that. You can grab HTTP method redirects or methods and filter based on those and understand where your anomalies are based on such logs. Speaking of anomalies, look at log statistics. So if you ingest your logs into something, this is the elk stack using Kibana, which is an open source and freely distributable engine similar to Splunk. What this does is allow you to make filtration saying, hey, I have an anomaly right here at this time and this date, hopefully in UTC. You convert it and understand if you had surely an application level issue, perhaps an issue around brute forcing, which I see is hitting the admin page for WordPress, and other distinct details. So if you have 0, for instance, and you don't expect any traffic whatsoever to that page because of firewall rules or other kind of compensating controls, all of a sudden you see 2 or 3 right here at 12 p.m. might be a sign of an issue that you need to look into. Now let's look at the remediation best practices. So troubleshooting network connections could be a result of bad architecture, bad practice, and something we want to avoid altogether so that we always have as much of that hammered out as we can. First, even though systems hardening is focused around security, we have something called CIS benchmarks. We also have other standards such as the NIST series, PCI series, and there are many different hardening standards and requirements. Usually these are created by third-party agencies, government as well as private. They give you best practices around what they found should be across security requirements across many different operating systems, solutions, and different technology vendors. The easy part is they give you these benchmarks and baselines on how to look for it. The hard part is you have to pay for someone's got to actually implement them, test them, patch and tune. But here's where they come in for a better troubleshooting and performance reliability to your end staff. Not only are you helping to secure them, you can support the requirements support patching, having minimal installs for footprints, and having high availability, which are key factors to understanding that you can have increased performance and then lowering overall cost and having the better resiliency that you need for scaling up for your end user's experience. Next, we have change control. So almost every organization uses change control. There's some sort of approval process, and there's usually a CAB, which is a control advisory board, or a change control board, CCB, depending on how you actually pronunciate it. The whole point is change control is to make sure you have auditing and accounting and ensure that you're doing testing, rapid testing, to make sure that you have as much of the kinks worked out as possible before you deploy to something in production. You want to also have rollback plans. If you don't have change control in your organization, look at this flow right here. If you have various processes such as updating firewall rules, you want to have change control. Start a change request, record it, exactly what you're going to do, the impact, and submit it to the board. If it's not approved, then go back to your drawing board. If yes, make sure you log everything that you've been doing, have a rollback plan, and ensure that you have the capability of testing with user acceptance whenever possible. And all that seems like a really simple workflow. Oftentimes, your connection, such as a firewall, is integrated with many other dependent systems, network engineering, routers, switches, as well as IPS and everything else. So anything connected to the network, you bet there's going to be a large change control and high scrutiny on what you do with that change. There's also architecture refactoring. Let's say you have a monolithic application that has everything. You've built out everything in there and the application just runs. Well, if you change something here, sometimes it can impact performance here or even up here. What you want to do is decouple them as much as possible, having loosely coupled architecture as opposed to tightly coupled architecture. Having APIs instead that different teams work on and manage and focus on high availability and reliability on each API, as opposed to having one team focus on everything under the sun under a single piece of software. Naturally, there's database specialty experts, there's API experts, security experts, so they work better in a decoupled environment, and you can actually have hybrid. So this part could be all cloud-based, which is AWS maybe. This could be on-premise. So it depends on your architecture. And now you can have hybrid capability, which this API might need the most resiliency as opposed to these APIs. You won't have that in monolithic architecture. So it's important to keep in mind that going to microservices or serverless architecture types are enabled by cloud solutions or highly resilient DevOps teams. Now let's take a break and go to our demo and really understand how we can do troubleshooting of connections as well as application payload at the log level. Hi, and welcome back. I hope you had a great break. Let's continue our lecture on getting a quick demonstration on testing basic normal behavior patterns and seeing if we can reproduce it or fix it whenever possible. You can use, in your labs, you utilize different tabletop exercises, and while there could be a bazillion solutions to one problem, you can narrow it down to really figure out what is the most feasible problems and likely capabilities. This requires experience in playing around. Let's start our connection here. And let's say I'm going to look for anything related to portquiz.net because they have lots of open ports for me to test. So using 216 on average. Although that's not a guarantee I'll keep using it. Let's try that instead. Host. And then go and tune back from that host. And because I love PowerShell, maybe I want to do a port scan. So maybe I want to port scan 1 to port 20, port 25. I can pipe that in here and actually do my own port scanning using testnet connection port here and a computer name portquiz.net. Or in this case, I'll use the hosted IP here, 5247.209.216. And this is basically saying I'm using Nmap for scanning it sequentially 1 through 25, piping it to a for each loop, and then off we go. And now I'm getting all kinds of information. And the funny part is it's sending net BIOS information as well for attempted name resolution lookup. Port number 2 is open true, which is kind of interesting. Now all this is doing is creating an initial socket, and it's actually not pulling any other information. There's no data being passed through. This is all at layer 4. And these ports are open, which is kind of good. And while I understand that these ports are open, maybe I don't want to, let's try to find a port that isn't open. I'm going to Control C and restart my capture. Maybe if I want to use Nmap instead, and I want to test a very specific set of ports. 22, so let's try 2040. Let's try 65,000 instead. We'll use 52, 47, 209, 216. So I have filtration on 22. And notice here, it's a little different output, but here, look at what we have here more importantly. Troubleshooting our connections here. We have a send and more sends. So we have 2 retry attempts from my application because we have double sends coming from the same port. And notice that the source port only increments once, but my destination ports remain the same. I have no send ACK as a response, which means what? I'm either filtering something potentially outbound, maybe, or I could be having an IPS blocking inbound on their side, maybe. All I know is I'm not getting anything back. But if I do instead of a send scan, which is send half open connection, maybe I want to try to connect to it directly. Let's clear that out. And now they're open. So what was the difference here? Here I was sending a send scan and hoping for a send and not doing not providing the ACK back. If I do a TCP raw connection, now I got open TCP handshake here. How do I know? Let's look. Destination port, and I should have a flag information according to SYN. Flags SYN and ACK set. And here's my SYN ACK, see, 22, 65, 535. And now we have our acknowledgement for the connection. And because I made that following acknowledgement towards the connection, notice that I had something interesting happen here. They both say open. I have my opens in my follow 22, and then I have a TCP reset basically saying no more connections. So we can actually look at here and saying, well, maybe the IPS is filtering here for any kind of scan related items, and then maybe they're not filtering for actual legitimate three-way handshakes. Could be a stateful firewall issue at that point. Really important way of troubleshooting in that case. How about we do something a little bit different, such as, remember I said there was all kinds of ports and protocols that can run on top of each other? Well, couldn't DNS run off of anything but 53? And the answer is sure. What about UDP? How do we know if it's not going to give me a response based on default behavior? Well, let's take a look. Let's try to go and connect to our famous 1122.3344. We'll say host. And then we'll do a ping. We'll see our echo out going in, but we don't have a reply. And we're getting a timeout. Now we're getting an ICMP message saying what? No response seen. And for some reason, we got an ICMP saying no response, which I thought was kind of funny. Okay. So we have no ping. What else can we try? Well, maybe we should start off with a, if ICMP is not coming through, maybe we can start off with a trace route. And you can actually do a trace route using mmap, using that TAC-TR, and using a particular port. So we'll try 80 and 443, which are common ports for web services on the web. And we'll resolve it, and we'll only show open ports. Now we're seeing our 80 and 443 go out, and only SYNs going back out. We don't have an actual SYN ACK response. Really, really interesting. Let's make sure we actually would not ping him. And now when we're trying, we're getting an echo ping request that we're sending out, which I think is kind of funny, and saying filtered, and no trace route is happening here. Really interesting. So at this point, nothing's going to happening, and if we test our own internet connection that we can get out to the web, that's obviously true. Then what is going on? Well, we got to dig down into maybe perhaps another type, and maybe not be restricted to only protocols. And since we don't have the logs on 1122.3344, we can't look at that either. So another way is let's validate if that IP address is even valid. We want to do IP Armin who is for North America. And we want to see if there's an actual IP address associated with that block. Is that a real IP? Oh, and it's a DoD network connection allocation. So it's a real IP and it's routable, but perhaps we shouldn't expect it to have any kind of open connections. And they own the entire /8, which is kind of interesting. Let's go to Shodan and utilize open source intelligence to see if anyone else has scanned them and see if there's any kind of ports open. It looks like we don't have any information about the results related to 1122.3344. The funny part is someone else has referenced in Taiwan a URL referral. It looks like an old redirecting document, perhaps with a fake address for the sake of something to put in there for debugging purposes. So we know it's owned by the DoD is routable, but we shouldn't expect the port to be opened at all. So it may not be the fact that we even have a route issue. We probably just don't have ports open, and we shouldn't be accessing anything, and no one knows anything about open ports related to that IP address. Really cool. How about let's try UDP? Well, let's look at our open source intelligence information, 888, which is common for Google's public DNS servers. It has an RN information, it's owned by Google, and it has known open ports on UDP with recursion enabled. But does it know anything about TCP? Well, let's see what we can do with Google's UDP 888. Let's recapture it on only Google's IP address. Oopsie, too many 8s. I'm going to capture over UDP. And then we're going to say hello. But we didn't get a response. So how do we know that it is UDP? Well, let's go Control C. Notice that there's no reset. And let's look up. Set my server to 8888. And let's look up google.com. Now we're getting the query because what did my query look like? Well, let's follow the string. I'm saying, hey, go find me this and give me the responses. Here's my response. And it's giving me that accordingly. It's coming from Google. Notice that that's the query. When I look at my UDP datagram, that's all it has. And then it has different flags related to the resource queries. So that's how I know there is. So you have to actually know the actual client to the port protocol level. What about TCP? Do we know anything about that? Well, one thing that we can do that force TCP inside DNS local client resolution is to use set VC, which is set virtual circuit, and then use XTIC systems, perhaps nothing that's cached. Now we're using TCP. Let's look at what we have here. We have our SYN flag, SYN-ACK, and ACK, so we know there's a full connection being made. And of course, we have the same information that we have here from my domain. And notice that there's no open source intelligence about TCP, only UDP. So start with what people know. So it's showed in HQ, or IO is actually the new one. Punch in an IP, see if there's any ports. And then finally, check to see if we have routing conditions. And so we started at layer 4s and layer 3s, and once we validated that, we actually worked our way up to layer 7. Layer 8 would be a human problem. I guess that is a layer. And that we understood that we had to really understand the protocols and normal behavior of different protocols, even at the application layer, to get a stimulus response. So that's it for this lecture. In the labs, you'll be doing different versions of this and trying to estimate how to resimulate, correct this if you had issues, and create hypotheses on what could be the issue to start with. Hope you had a great time and you're enjoying the lecture so far. We'll see you in the next one.